Hey everyone, my name's Max, and today I will be talking about shell structures as a case typology for understanding lightweight structures. To develop this understanding about the nature of shell structures and why they're significant for lightweight structures in general, we'll be investigating into a few areas of learning, including teaching, research and literature, testing and simulating, as well as evaluating the outcomes of these learnings. Before we analyse complex structural forms, let's start with the basics. In our first week, we learned about the foundational building blocks for structures and analysis, and established the role of elements and their behavioural relationships with applied forces. In our second week, we learnt about approaches to analysis, including practical simulation techniques, as well as calculating behavioural predictions based on structural parameters. From there, we were able to comprehend analysis and optimization techniques like form finding and rationalization in our third week. Now let's look at examples from the prose to paint detail onto this learning picture. Our first study here provides us with definitions to our key fundamental variables for relevant elements in shell structures, which offers us clarity for factors that are necessary to consider when we're doing structural analysis, enabling us to use predictive calculations, as well as CAD calculations for automation. Next, let's find a study that illustrates broader techniques that are more suitable for real-world applications. This one shows us examples of thinking involved in developing shell structure design processes that are suitable for ideal fabrication outcomes. By testing the role of analytical definitions for hands-on fabrication, we can identify outcome issues which point towards challenges involved with relating theory and calculation to practice and delivery. This study highlights where these challenges arise. For the third study, let's take a look at what kind of research is behind the definitions and finite methods that we use. This paper investigates calculation issues that emerge in existing research, like findings from the last paper. Developing deeper relationship definitions based on known problems is effective for improving form-finding calculations, and establishing improvements like these increases our confidence in the comprehensiveness of our analysis and optimizing methods when we conduct iterative testing and simulations. Now it's time to think about the implications of the content within these investigations for undergoing our own projects in developing lightweight structures. For one, we know that analysing and optimizing unique structures like shells requires a few tangible things. Before analysis can even begin, we need a lot of defined parameters within our structure, including the specifications of those. For any typology, this includes specifications for the elements which the structure is made from, and the boundaries that define spatial limitations. In order to execute this analysis, a researcher also needs to be equipped with the knowledge for calculating outcomes from these parameters. For us, this is much easier with design automation tools. The outcomes of fabricated shell structures in particular present various positives and negatives. Most positive outcomes can be credited to two main categories, being aesthetics and optimization between material and structural performance. On the other hand, most practical negatives relate to project processes having issues with design complexity, affecting building development and costs. Moving on from the abstract realm of definition for these designs, let's take a look at some shell structure buildings which visibly demonstrate the consideration of these structural features. First up, in our Australian front yard, we have the Sydney Opera House. When you look closely at the exterior tiles covering the Opera House's facade, you'll notice an array of lines which match a rationalised subdivision of the surface into smaller, flat components that can cover its exterior. Next up, in the UK, we also have a botanical greenhouse that features an almost organic-like appearance for its bubble-like facade. Considering its primitive 3D form is made of spherical surface sections, its load-bearing behaviour matches that of simulated form-finding techniques with defined edge boundaries. Most obviously, it resembles techniques that use inflation. In Canada, we have another sphere-based shell structure. The Montreal biosphere gives a highly delicate appearance thanks to its seemingly very thin structural elements as triangulated beams and connection supports. The impression of this dome stability defying its appearance of sturdiness is a great demonstration of the extent to which analysis for the element properties of shell-like shapes can allow designs to push the boundaries of structural requirements without compromising on necessary performance. Now, for a quick recap over the investigation so far towards understanding more about shell structures, I'll re-mention some of the key learning areas before moving on to testing any methods. In structural engineering, we have conceptualized variables affecting structural performance. In shell theory, we have more specialized approaches towards form-finding techniques specifically for shell structures. In computational analysis, we have an understanding for the usefulness of tools that can automate analytical tasks. In materials science, we can relate physical concerns in fabrication to conceptual relationships. In construction techniques, we can consider how the outcomes of shell structures perform within a practical context. And finally, in architectural design, we can appreciate the potential for geometric computation to offer unique and interesting building designs and solutions. Now that we've established foundational knowledge for testing with available analytical techniques, let's put it to use by applying these definitions and approaches to the design of a shell structure. Thankfully for us designers, we have access to computational tools which can automate many of the necessary calculations and relationship definitions within these processes, and so we will be simulating analysis within our Rhino Grasshopper software. To establish goal outcomes from these workflows in our current design progress, we will base one scripted method per deliverable. 1. A form-finding script for the shape of a shell structure. 2. A wireframe script which provides the geometric data that correlates with structural elements. And 3. A 3D model script which provides a visualized model with clean geometry for fabrication. To find the form of a structurally optimal shell, our script will aim to simulate a stretchable fabric sagging in the upwards direction. To achieve this, we'll start with a flat triangulated mesh to simulate a fabric-like structure, and with supports defined, we can then apply forces to the structural connections and see what happens as a result. To make the script workable for varying contexts, the support definitions facilitate individual changes in location and size, with placements and mesh transformations being applicable to any ground level boundaries. Using the Kangaroo extension for testing calculations, we now have the form of a geometric shell derived by simulated forces. Now that we have a form, the next step for structural analysis is to define structural elements. To derive elements from the mesh form, we can refine the mesh for more precise geometry, representing a smooth structure. Then extract geometry data that can define necessary structural elements. At this point, we can produce a refined mesh as a shell input and point locations as support inputs for future analysis in Karamba. With a refined wireframe mesh, we can create a 3D version of the form that we fabricated. This process will require manual modification to baked geometry, starting with the mesh, then extruding it along the Z-axis, then cutting its base for a flat bottom. From this, we now get a clean 3D geometry component contained as one closed object. With these three scripts, there are some matters to address regarding their strengths and limitations. The strengths of these scripts include reliable output integrity with changing parameters such as boundaries and support properties, component selection being optimized for script calculation efficiency and speed, and for a script that adjusts form for any given boundary has a good degree of parameter control. On the other hand, there are some notable drawbacks to this script. The boundary correction method isn't structurally optimized and will negatively affect how optimized the structure is. The script is designed for holes in the boundary and breaks when there is no hole. And not that this is significant since the approach here is adjust the form based on desired support locations, but there's no additional option to automatically optimize support placement positions for a given boundary. Despite some technical shortcomings, the usefulness of scripts like this and more developed scripts is very significant for design processes. Automating calculation tasks and containing concept definitions in computerized tools makes testing in analysis and design vastly more efficient and in many cases better optimizes the accuracy of outcome predictions. So, to bring everything together, our investigations into structural typologies span across various collections of things to consider for their designs. Through teaching, we learn from those who can offer us direction for developing our understandings of concepts affecting our designs. Through literary research, we can refine our understandings with deeper conceptual considerations and examples of how we might want to approach research into further examination. And through testing, we can engage in the practical application of what we've learned to relate our abstract conceptualizations to realized results. And with that, thanks for hearing everything I have to say about shell structures, and I look forwards to seeing the future of computational design as we build upon these learnings as a community.